Hello AP Chem students, I hope you're all doing well. The purpose of this video is to basically finish up the remainder of the content that is unit topic 6 on the AP Chem curriculum. So we've already covered chapter 5, section 6, which covered calorimetry and heat capacity. So today we're going to talk about bond enthalpy and enthalpy of reaction. So here's the definition. Bond energy, also called mean bond enthalpy or average bond enthalpy, is the measure of the bond strength in a chemical bond. So here is a picture of a table listing the average bond enthalpies of various chemical bonds. For example, 413 kilojoules of energy is required to break 1 mole of CH bonds. Conversely, if 1 mole of CH bonds form, 413 kilojoules of energy will be released. So as we talked about before, when we talked about activation energy and we compare the energy of the products to the reactants and so forth, when a chemical reaction occurs, bonds are broken and bonds are formed. Energy is required to break bonds, and energy is released when bonds form. Bond energies can be used to estimate the change in enthalpy of a reaction, and I'm going to show you an example here down below. Determine the enthalpy change of the following reaction. So we have C2H4 plus H2 forming C2H6. So in order to figure out the bond enthalpy of a reaction with bond energies, I think it is best to go ahead and draw out the structures. So I've done that below. Using your knowledge of Lewis structures, C2H4 looks like this. Hydrogen's diatomic, it's going to look like this. And C2H6, ethane, is going to look like this. When this reaction occurs, this C double bond C, this double bond here between the two carbons has to be broken, and these two H's have to be broken apart. Once we break this double bond and break the H's then are free to attach themselves to the carbon right here, and then those carbon atoms are going to form a single bond between each other. So on the reactant side, bonds are being broken. The double bonded C is being broken, and the HH bond is being broken. On the product side, we're going to form a CH bond right here, a CH bond right here, and we're going to form a single bond between two carbon atoms. The enthalpy of a reaction is equal to the summation of the energy required to break the bonds in the reaction minus the summation of the energy released by the bonds being formed in the reaction. We can represent that with this equation right here. The enthalpy of a reaction is equal to the summation, that just means the total, all added together. It's equal to the summation of the bonds broken minus the summation of the bonds formed. Rxn is used to represent reaction or R. So the enthalpy, change in enthalpy of the reaction equals the total amount of energy required to break the bonds minus the total amount of energy from the bonds that are formed. So I pulled these values here from off the chart that I have shown you above right here. So to make it simple, I just pulled them out of the chart. But this chart right up here, I pulled out the bond energies that are needed to complete this problem. So to break that one double bonded between the two carbons, it takes 614 kilojoules of energy. An HH bond, it's going to take 436 kilojoules of energy. So on the reactant side, it's going to take 1,050 kilojoules to break the bonds involved in the reaction. On the product side, we're going to form a single CC bond, and we're going to form two CH bonds. So the energy that's going to be produced from forming those bonds is 340 kilojoules from the CC bond, which is shown right up here. And we're going to have 413 kilojoules, which is the bond of a CH bond. We multiply that by 2 because we're going to form 2 of those bonds. So the amount of energy that is being used to break the bonds is 1,050. The amount that is going to be produced is 1,174. So if we do the simple mathematics, we find out that the change in enthalpy for the reaction is equal to negative 124 kilojoules of energy. So a negative delta H, as we talked about previously, indicates an exothermic reaction. So the change in enthalpy for the production of C2H6 from C2H4 and H2 is 124 kilojoules per mole. All right, let's try another example. Using the provided bond enthalpies, calculate the enthalpy of reaction for the combustion of 1 mole of methane. So hopefully from your previous work in honors chem, you recall that a combustion reaction requires oxygen and always produces carbon dioxide and water. So the balance equation for the combustion of methane is shown right here. 1 mole of CH4 plus 2 moles of water will form 1 mole of CO2 and 2 moles of water. I'm sorry, I said that wrong. 1 mole of CH4 plus 2 moles of oxygen will form 1 mole of CO2, 2 moles of H2O. So to calculate the enthalpy of this reaction, we're going to go ahead and use the bond energies listed over here. I've highlighted the bond energies that are going to apply to this particular reaction. So as I mentioned earlier, I think it's easiest to go ahead and draw the structures out. So this is what CH4 looks like. It basically has 4 CH bonds. The reaction calls for 2 moles of oxygen. We call oxygen is diatomic, so I need 2 moles of O2. O2 is a doubly bonded molecule. On the product side, we're going to form CO2, which means we're going to form a CO bond here and a CO bond here, and note that is a double bond. We're also going to produce 2 moles of water. So the bonds that are going to form water is we're going to have an OH bond here, an OH bond here, another OH bond here, and another OH bond here. So we'll have a total of 4 OH bonds. To calculate the total amount of energy or the enthalpy of this reaction, we need the total energy required to break the bonds, and we're going to subtract from that the total amount of energy given off when the bonds are formed. So from our diagram, we're going to take the bond energy of CH times 4, so we have 4 CH bonds. We're going to take the bond energy of double bond oxygen and times it by 2 because we have 2 moles of oxygen. So in order to break these 4 CH bonds and these 2 molecules of O2, it's going to take us a total of 2,642 kilojoules of energy. So I'm going to put that on hold. Let's focus on the product side. We're going to form CO2. CO2 involves 2 CO bonds, and these are double bonds. So looking at the chart, I'm going to take the bond energy of CO, which is 799, I times it by 2. We're also going to produce 2 moles of water. Now note, for 2 moles of water, there's 1, 2, 3, 4 OH bonds. So I'm going to take the bond enthalpy of OH, and I'm going to multiply it by 4. We're going to find out here that the amount of energy given off when the bonds are formed is 3,450 kilojoules. We complete the mathematics. I take the amount of energy taken or required to break the bonds of 2,642, subtract the amount of energy that's going to be given off by the formation of the bonds, and we get a value of negative 808 kilojoules per mole. Now recall, a negative delta H in a reaction indicates that the reaction is endothermic. So this reaction will be exothermic, producing 808 kilojoules per mole of CH4. And that is pretty much how you calculate the enthalpy of a reaction based on enthalpies of the bonds or bond energy. I also suggest that you watch this video here. They do a great job explaining the same topic. So if you're struggling a little bit with this, then go ahead and watch this YouTube video.